Now, in the previous video, we talked about nuclear fission, and we realized that if we can have neutrons with sufficient thermal energies, and when we bombard that neutron on a uranium nucleus, it has a probability of going into a state of instability, and once it is unstable, it breaks down, and you have two daughter nucleuses, and you have additional neutrons. So this is what is referred as nuclear fission. So splitting of a parent nucleus into the daughter nucleus with addition of energy and neutrons. Now, now this kind of thing that we have in nuclear fission is that we have three neutrons. Three neutrons are produced, and they are produced along with the release of large amount of energy. Large amount of energy. So in our case, it was nearly 200 mega electron volts. So these newly produced neutrons that we have, if we take them as target particles here, as neutrons, they can cause further fission of more nuclei. So suppose here is another uranium, another uranium, another uranium. So what we will have is we will have again barium and krypton, again barium and krypton, again barium and krypton. So barium, krypton, barium, krypton, okay, and barium and krypton, and then we will have additional 3 neutrons. Now this process can continue. They will interact with more uranium atoms, and the process continues, and the number of fissions taking place at each stage, it goes on increasing at very fast rate. And this is what is called as uncontrolled chain reaction. Uncontrolled chain reaction. And however, if we have to maintain this uncontrolled chain reaction, there are a couple of difficulties that come across. Now let us see what kind of difficulties can come across. If we talk about the ordinary uranium, I mean uranium, it consists of three isotopes. And what are they? That's uranium-238, then uranium-236, then uranium-235. Okay, they all have same atomic numbers. That's 92, 92, and 92. And out of these three, this uranium-238, it's in abundance. It is nearly 99.3% available. And 235 is nearly 0.7% available. And 236 is it's very much rare, less than 0.1%. And this uranium-238 that we are talking about, it needs it can be fissioned only by fast moving neutrons, and their energy should be, if we have a neutron, its energy should be 1 mega electron volt. And even more. And neutrons having low energy, they are simply absorbed by this uranium-238, and hence chain reaction cannot take place. The chain reaction that I talked about here, where we have multiplicity of nucleuses, and there is a rate going on, and there's no control, and the reaction can trigger, and if it triggers, it goes very fast. So if this energy of the neutron is not sufficient enough to cause disturbance to uranium-238, then even the reaction will not start, and it will not sustain. Now, this uranium-235, talking about uranium-235, This can be fissioned by even slow neutrons. We can fission it using slow neutrons, and to sustain the chain reaction, if we have to sustain the chain reaction, this uranium-235 is separated from ordinary uranium, so we have to filter it out, and different methods are applied to do this. And uranium-235 so obtained is called enriched. It's called enriched uranium. All right. So the point is clear here that the reaction can be triggered simply by slow moving neutrons if we have uranium-235. And what we have is we have to liberate uranium-235 from a bulge having all the three isotopes in it. And once we are able to separate out uranium 235, we call this thing as enriched uranium, which is fissionable. This uranium is fissionable. The fission of the enriched uranium is possible with both fast and slow neutrons, and hence we can have a chain reaction. And this chain reaction that we talked about, this chain reaction can be sustained. Now, another important thing about another method, rather, we can talk about to sustain this chain reaction is to slow down the neutrons. Once we have the neutrons coming in a reaction, and we can slow down these neutrons emitted in a fission, and the chances of causing this fission of uranium-238 that in principle by slow neutrons are very small, as we talked about, and hence these neutrons are available for fission of uranium-235-92, which are slow. And the fast neutrons can be slowed down by certain materials which are commonly known as moderators. So you have to slow down these neutrons so that the fission can take place in uranium-235. Now, what's a moderator? The moderator is basically talking about this moderator. Now, what is it? This moderator is most effective if the mass of its atoms is about same as that of mass of neutron. So mass of neutron is same as that of the mass of the atoms that are used as moderators to slow down these fast moving neutrons. And ordinary water can also act as moderator. But it's not used as moderator because it often absorbs neutrons. It often absorbs neutrons. Hence, chain reaction can ultimately stop. Can stop. And if we talk about heavy water, heavy water is made by an isotope of hydrogen called deuterium. So that is H2N1 and is written as D2O. Okay, it is more effective moderator than graphite because deuterium in it is lighter than the carbon nucleus in the graphite. Okay, so carbon nuclei and H2I nuclei. So it is lighter than that of carbon nuclei that we have in graphite. So deuterium slows down the fast-moving neutrons more effectively. So that's the case. Now, the important point here is that the neutrons emitted, that the neutrons that we have that are emitted during the fission, they are very fast, and they can travel a large distance before being slowed down. Now, if the size of the fissionable material, talking about the size of the fissionable material that we have, if that size that we have, if that size is small, the neutrons emitted will escape, and they will escape the fissionable material before they are slowed down. Hence, the chain reaction cannot sustain. So, what is important is that the size of this fissionable material, this size, should be larger than that of some critical size. So we have some critical size for this fissionable material from where a reaction has to be started. Now, this critical size is calculated by a factor. This critical size is calculated by a factor, critical size of fissionable material, and that factor is symbolized as K, and this factor is called as a reproduction factor. It's called as reproduction factor. That should be the case. Okay, so this factor will determine whether or not any mass of fissionable material will sustain a chain reaction. Now, this K is what? It is basically rate of production of neutrons divided by rate of loss of neutrons. Now, if this K comes out to be 1, that's the rate of production of the neutrons is equal to the rate of loss of the neutrons. The mass of the fissionable material is said to be critical mass. Now, here we have critical mass of fissionable material. And if this K is less than 1, then the chain reaction simply stops. Then this chain reaction stops. Now, we have two types of chain reactions. And what are they? One is called as uncontrolled. One is called as uncontrolled chain reaction. Now, what is uncontrolled chain reaction? If more than one neutron produced in a fission cause further fission at each stage, then the number of fissions and energy released is simply multiplied. That's true. Simply multiplied. And it's multiplied rapidly. Such a reaction is called uncontrolled reaction or uncontrolled chain reaction that I showed you in the very first page. This is an uncontrolled chain reaction. You hit the uranium, you have neutrons. All the 3 neutrons will hit coming uranium atoms. Then there will be exponential rise in number of neutrons hitting the nucleuses that they are facing. Now, this kind of reaction is called as uncontrolled chain reaction, and in such chain reactions, huge amount of energy is released within a fraction of second. And this is basically the underlying principle of an atom bomb. So atom bomb is basically it is an uncontrolled chain reaction. Now, for controlled chain reaction, if only one neutron is available to cause further fission, so I would like to demonstrate here controlled chain reaction. So what I have, suppose I have uranium, it's going to give me 3 neutrons, okay? 2 of the neutrons will waste, but the one coming out here will make fission, and I will have barium and krypton. Again, we will have 3 neutrons, 1, 2, and 3. They will not do any job, but this one will instigate the process, and again we will have 3. So how to generalize this thing? Now if only one neutron is available to cause further fission at each stage, then the constant amount of energy is released in this case. We have constant energy in this case. Such a reaction is called as controlled chain reaction. And this controlled chain reaction takes place in a nuclear reactor. That nuclear reactors that we have, and the energy obtained from such a reaction is used for the peaceful purposes, not for the purposes like that of atom bomb, which is a destruction for the world. And there should not remain a single country to have this atom bomb, and we must have freedom from this kind of nuclear weapon, which can not only destroy the mankind, it can destroy all possible life on the planet, and it can damage the genes. It's very, very crazy thing, and there should be no way for it. And nuclear reactors, they certainly are. They are for peaceful purposes, and they give a lot of relaxation to the people who are energy deficient. So to say, this is a nuclear reactor.